And so one of the first topics that we'll do, in the 2 lectures, the first topic will be a classic problem called SSSP, which is single source shortest paths. Single source shortest paths. So given 2 vertices, remember that we said the dist SV is the shortest path distance from S to V, except and we discussed that we could solve this using BFS, but BFS works for unweighted graphs. So what this means is, here the shortest path distance is simply the number of edges on the path. Right? That's what we were doing, right? We were just counting how many edges were on the path. But if you were to think of a scenario like Google Maps, which actually is doing shortest path computations, observe that these edges actually have weights on them. Edges may have different weights. So what is the weight? So think of it as, and so we denote this usually as WUV, this is the weight. You can think of this as like maybe some kind of like distance in miles between UV, maybe it's a distance in time. It could be the amount of time that it takes. It could be anything, but it's some number called the weight. And usually we'll think of directed graphs here. So the weight of going from U to V and the weight of going from V to U are different. Right? So these things could be different. There's a weight of going from U to V, a weight of going from V to U. And the way this is often stored is if you look at the adjacency list, you can kind of store it in that linked list. So your linked list has more data. So for example, if this is the list for U, you could have maybe V, and then you store the weight inside. And then you have some other vertex X, and you're storing the weight from U to X, and so on and so forth. So the weights are kind of stored in the nodes themselves. And so we could look at I'll call it the weighted length of a path SU1, U2 going to V. So if you have some path from S to V. So in this case, I'm considering things to be directed because that's usually the use case. This is the sum over all I going from 0 to, let me call it, excuse me, UK minus 1. So I'm just going to denote this as UK, and this is U0 just for convenience. This is going to be the weight of UI to UI plus 1, right? That's just looking at the sum of all of these weights. That's the length of this path. That is the length of this path. So that is the length of a path, and then you're trying to find the path of the minimum length. Does this question make sense? Any questions about the problem itself? Okay. Now note that weights may be negative, in which case the distance of U to V might not be defined. Okay, so I have to explain what this means. So you think that you always have a notion of a shortest path, but suppose I have this graph over here. And we could even consider this graph to be undirected. Okay, so we'll consider this graph to be undirected. And so I have 1, -3, 1, 4, 3. So what is the distance from S to V? What is the distance? Someone want to take a guess? What is the distance? 8. So you went 4, 1, 3. But I could do better than that. I can do better than 8. 5. Okay, you can go to 5. You go 4, 1, -3, and 3, and you get 5. I claim you can even do better than 5. It's a bit of a trick question, though. But if you
can run around in a circle and get many -1s in the circle.
I'm sorry, say that again?
You can get to like -infinity by running around in a loop.
Exactly, right? You could go here and you could just keep cycling around this, because every time you cycle around this, your distance decreases by 1. You keep cycling around this and finally go there. So the distance, it seems to be something like -infinity, because the more times you go around the loop, the lower your distance becomes. And so this is a problem, because in some sense it means that this distance isn't really well defined unless you consider paths that don't intersect themselves. But then you could consider that. But in general, when there is this sort of a situation, we say shortest path distances are not defined. Does this example make sense? Excuse me. So when there are negative weight cycles, so a cycle is that structure over there. Okay? So when there are negative weight cycles, the distance is not defined. And this is called a negative weight cycle. So when you have negative weight cycles, distances are not defined. But as long as you don't have negative weight cycles, distances are defined. And you could ask, find me shortest path distances in a graph. And this is a very, very important and classic problem. It appears over and over again. So the simplest example that you would be familiar with, although it's a complex algorithm to do so, is for Google Maps, which finds shortest paths when you want distances. There's routing in computer networks where you want to find shortest paths. Often the weight might be some kind of latency, and you want to minimize the latency. And so you have many, many different kinds of problems which can be cast as shortest path problems where there are weights. If there are no weights, you can use BFS. But when there are weights, the problem becomes more complicated. BFS doesn't work any longer. Okay? So the way that at least the algorithms we will talk about work is they have a very specific pattern. And this is all inspired by breadth first search. So SSSP, just as before, maintains 2 arrays. We will again assume that V goes from 1 to n for simplicity. So the first array, and it's single source because the source S is fixed. This is just like BFS starting from a single source. Excuse me. So what this maintains is it maintains 2 arrays. So I'm going to refer to this, the first one, as est of V. This is an estimate of the true distance from S to V. It's going to maintain an estimate. And this is really going to be like the distance on a tree, just like BFS. And the second is something called the predecessor, which we know and love, which is basically the parent of V on shortest path tree. From S. Okay? So just like you have BFS maintaining these two arrays, single source shortest path algorithms maintain two arrays. They're slightly different. So one is the estimate, which is the current best estimate, and the next is the predecessor, which is the parent just as before. Okay? So I'm going to write one more thing and then I'm going to end. So remember that the predecessor is maintained some kind of parent. So we have some parents as before. Now, it's going to build this tree slowly, but it's going to be a lot more complicated than BFS. But it's going to maintain these invariants. So these invariants are properties that are going to be true at all times during the algorithm. What does the last word say in 2? Oh, I'm sorry, this says from. So what are the invariants? The first invariant is that the estimate of V will always be at least the true distance. And the second is that if you look at V, predecessor of V, the predecessor of the predecessor of V, this is not the output. This is actually at any intermediate stage. All the way going back to S, this is a path in reverse from S to V of length est of V. It's just a fancy way of saying that if you look at whatever path you have, the length of this path is going to be your estimate. Right? So you're simply maintaining S to be the length of that, and this is always going to be at least. Eventually, you want this to be equal. When the output, in the output, one is going to simply just say that the estimate of V is equal to the distance of V. When you want the output, you want these to be equal. But the way the algorithm works, it starts with an estimate, and it's going to keep improving upon the estimate by looking at different paths, and it's going to maintain some shortest path tree. And this is how this algorithm proceeds. So this is a good time to end. When we come back in the next lecture, I will explain single source shortest path algorithms. I'll explain the Bellman-Ford algorithm and Dijkstra's algorithm. But for the purposes of homework 4, you already have everything that you need to know. Okay? So I'll end here. I'll take some questions over here, and then we can talk more during office hours.
Your office hours are at 5:30 and 6:30 on Wednesday?